Swayam Prabha. Digital India. Educated India.
So you see, let us try to sum up what we have come up to so far. You see, we are trying to prove the the four-vertex theorem, all right? And so what we have done is that we have taken the arc length parameterization of the curve, all right? And so L of gamma is the length of gamma, and so gamma is gamma of S. S is the arc length. Okay, and then of course you have you have the curvature function, the sine curvature function that assigns to every point on the curve the sine curvature, all right? And we want to talk about the vertices of the curve. You see, the vertices of the curve are they are the critical points of the curvature function. So that means that you would like to approach this from a calculus point of view, so you would like them to be thought of as zeros of the derivative. So of course, if you don't want to involve the differentiability of the curvature function, then you could have just been content with saying that you're worried about local maxima and minima of the curvature function. Okay, of course, if you have a function, if it has a local maximum or a minimum, and if it is differentiable, continuously differentiable, then at every point of local maximum or minimum, the derivative will vanish, so it will be a critical point. But of course, the converse is not true. A critical point may be just an inflection point. Okay, so what we the whole point about the four-vertex theorem is that if you take a curve which is first of all a closed curve, and that means the starting point is the same as the ending point, and it is also simple. That means it has no self-intersections. And you assume that it is smooth enough, at least to the extent that the sine curvature is defined. Okay, then there are at least two local maxima and two local minima. Okay, and of course they will be alternating. That is because between any two local extremum of one type, there will always be a local extremum of the other type. Okay, this is just guaranteed by topology. Okay, that if you take a closed interval and you have a continuous function on a closed interval, it will always closed and bounded interval of finite length, a continuous function on that will always attain a global maximum and a global minimum. This is guaranteed by topology. Okay, so so the moral of the story is that we would like to show that there are at least four vertices. If you want the more stronger statement, we would like to show that there are at least four local maxima minima. Okay, at least two local maxima and two local minima, all right? And so that is a four-vertex theorem. Now there are two degenerate cases that we don't want to think of, and the degenerate cases are when a portion of the curve contains an arc of a circle or an arc of a straight line. In both of these cases, what happens is that the curvature is constant, and so the derivative of the curvature is zero throughout that arc. Okay, and that means every point in the arc is a vertex by definition. and therefore you have infinitely many of them. So this is not an interesting case. So we are going to assume that the curve is such that no portion of the curve contains an arc of a straight line or an arc of a circle. So that's an assumption you make. The advantage of this assumption is that now if you take the curvature function, okay, and you take its derivative, so we would like to look at it from a differential geometric viewpoint. So we will take the situation where the curvature function is actually differentiable and in fact continuously differentiable. Okay, so you take the derivative of the curvature function. The derivative of the curvature function cannot vanish on any subinterval. Okay, because if there is a subinterval of the parametrizing interval where the derivative of the curvature vanishes, then it means that on that subinterval your curve has to be an arc of a straight line, or it should be an arc of a circle, which we don't want to take. Okay, so therefore the moral of the story is that you see the curvature function is not identically zero. I mean, its derivative is not identically zero on any subinterval. That is the same as saying that the curvature function is not identically constant on any subinterval. Okay, so it's always changing. All right, and therefore, so that is the assumption. And then what you have to show is that there are at least 4 vertices. In fact, you want to show that there are at least 2 local maxima and 2 local minima. Okay, and of course, the way to think about it geometrically is you should understand that the local maxima are in between the local minima. Okay, and vice versa if you draw the curve as a loop. Okay, you have to show that there are at least 4 vertices. So the cases you have to contradict are that there are less than 4 vertices. So you can have 0 vertex or just 1 vertex or 2 or 3 vertices. Okay, now because of topology, you see the curvature function being continuous itself, okay, and defined on this closed bounded interval, will tell you that the curvature function will attain a global minimum and a global maximum. Okay, and these global minimum and global maximum are going to be just the endpoints of the image of the parametrizing interval under the curvature function. So that means that there is already one global maximum, there is already one global minimum. Okay, that accounts for already 2 vertices. Okay, so what this tells you is that the case of 0 vertex or 1 vertex will not occur. Okay, so that 2 vertices are already given to you. They exist from topology. They exist by topology. Okay, you have to only worry about whether there could be 1 extra vertex. Okay, the case of 3 vertices. And the claim is that if there are 3 vertices, okay, and if there are just 2 vertices, both of them can be put together in a single case, and that case is that the curve, you see, can be broken into 2 segments where the signs of the derivative of the curvature, they are opposite. Okay, so to say that, you see, so let me remind you, we are proving the we are proving the case for a convex curve. Okay, and there is also, the theorem is true for even for a non-convex curve. Okay, and in fact a complete generalization of this theorem is also available, and it has been generalized to even curves on surfaces and curves in manifolds and so on. Okay, so it is a this theorem that was first initiated by Syamadas Mukhopadhyay in 1909. You see, for about 100 years it has given rise to amazing work, interesting work connected with curves. Okay, so it's a very beautiful theorem, and still there are some open questions which are still unanswered. Okay, which amount to convex curves on surfaces. Okay, or curves on convex surfaces, closed curves on convex surfaces. So you see, so it's a very, very interesting thing. But what we are going to do is first discuss only the convex case. Namely, you are assuming also that the curve is convex. Now I have already told you that convexity has 4 avatars, and the convexity can be given as any 2 points on the curve. If you take any 2 points on the curve and then you join the line segment, then every point in that line segment should either lie on the curve or in the interior. And then if you take any 2 points in the interior of the curve and then join them by a line segment, then the whole line segment should lie in the interior. Okay. Then if you take any point of the curve and draw the tangent, the curve is only on one side of the tangent, and this should happen at every point. The fourth thing that is important is what we will use is that if a straight line cuts the curve exactly at 2 points, okay, then it will divide the curve into 2 segments. Okay, and this is the one that we are going to use. In fact, there are many more characterizations. You can also make this characterization that you take a point in the interior of the curve and you take a point in the boundary of the curve and join the line segment, then the whole line segment has to lie, in the interior. Okay, so that is another characterization which uses one interior point and one point on the curve. Okay, now all these are equivalent. So the claim is as follows. The claim is, okay, whether there are 2 or 3 vertices, okay, see out of which at least 2 out of which 2 are certainly global maximum certainly global certainly a global maximum and a global minimum for the sine curvature of gamma. Okay, the curve can be divided into 2 continuous closed arcs such that such that the derivative of the curvature, if you take the sine of that is of opposite sign on these 2 arcs. Okay, so such that Ks gamma dot has opposite sign on these arcs. Okay, so this is a claim, and this is very, very easy to see. So you see, you have this you have the real line, and then you have this parameterizing interval from 0 to L of gamma. So the parameter is of course S, and you are sending it to gamma of S. So that is going to be that is going to be your curve. So I have to draw a convex curve. So let me draw a convex curve. Okay, so I have some point which is gamma of 0, and this is also gamma of L of gamma. Okay, this is a starting point, and then this is the ending point. And you see, you also have, so if you take any S here, I'm going to get a point here which is gamma of S. Okay, and then of course you already have a global maximum and a global minimum, so they are going to be attained at 2 points. Let me call them as S0 and S1. So S0, without loss of generality, you have this S0, you have this S1. So this is a point of global maximum for the sine curvature of gamma, and this point is this is a point of global minimum for the sine curvature of gamma. Okay, now so these are going to correspond to 2 points. So let me draw them here. So for example, so I will just call this as gamma of S0, and let me take some other point which is so this is gamma of S1. Okay, so now you see, so if you take the case of only 2 vertices. Okay, then these two vertices have to be at these points given by S0 and S1, right? Now you see at no other point the derivative vanishes, okay, the derivative of the curvature, the sine curvature, okay. Now so the derivative of the sine curvature vanishes at S0 and it vanishes at S1, and at no other point it vanishes, because wherever it vanishes, by definition where the derivative vanishes is a critical point, and we assume there are only two, and these two are certainly going to include the two which correspond to the global maximum and global minimum, okay. So in between at all other points, okay, so if you go from S0 to S1, okay, suppose you go from S0 to S1, then you know you are going to traverse this portion of the curve, okay, from S0 to S1, all right. And on this portion of the curve, what happens is that you know you are actually going from a global maximum to global minimum, okay. So essentially your curvature function is decreasing, okay, and perhaps the way I have drawn the picture, it appears that see at S0, you see the way at least as I physically drawn the picture, at S0 the circle of curvature looks large, so the radius of curvature is larger, therefore gamma S0 should be in principle the global minimum, okay. And if you look at gamma S1, at that point the circle is small, so the radius of curvature is small, so it should be a maximum. So let me change it just for the sake of the picture, okay. I will interchange the maximum and minimum, but the point is that you cannot draw such a picture. That is the actually the contradiction. So the picture, even with that adjustment, the picture is wrong. That's what we are going to prove. So let me just for the sake of the picture change it like this. Otherwise, I have to redraw the picture. So let me put maximum. Sorry, I put minimum here, and then I put maximum here, okay. And so you see now as you go from S0 to S1, you can see that the sine curvature is increasing, okay, and it never vanishes. It's a continuous function, never vanishes, and is increasing, and it's differentiable. Derivative is continuous, therefore the derivative has to be positive, okay, for an increasing function, strictly increasing function, okay, derivative has to be positive. So what happens is on this segment of the curve, you will see that Ks sub gamma dot is positive, okay, and so here I will get Ks sub gamma dot is greater than 0, all right. Now what about the other segment? As you can see, as you go along the curve, you are actually now going to go from a maximum to a minimum, and there is no other vertex in between. So that means that Ks dot of gamma has to be, it has to be negative, because it is going to be a strictly monotonically decreasing function, and therefore its derivative has to be strictly negative. So you are going to, so you are going to get this other segment. So if I draw the other segment, it's going to be, so let me try it with this. So the other segment is from here all the way to here, okay. So this is the other segment of the curve, and which is the red segment. So I think I would go all the way up to here, okay. So on this segment, what happens is that you are going to have that the sine curvature of gamma, if you take the derivative, it is going to be negative, okay. So basically what has happened is that I have this, if you want, you can think of I am interested in these 2 points. You see, I am interested in these 2 points which divide the curve into 2 segments. One on these 2 segments, the sign of the derivative of the sine curvature are opposite. So I am interested in these 2 points. So I am interested actually in this line, okay. So this is a point of maximum radius of curvature, minimum curvature. This is a point of minimum radius of curvature, maximum curvature, and that these 2 points, if you draw the chord, okay, or the secant rather, then it divides the curve into 2 segments. On both on 2 sides, on these 2 segments, you see the sine curvature, the sign of the sine curvature, the derivative of the sine curvature, that is opposite. That's what is very, very important. Okay. Yeah, of course. What I mean is, when you say opposite sign, you also allow 0. So if you want, one can put, greater than or equal to 0, less than or equal to 0. But what I'm very much interested is on the, if you forget those points, on the open arcs, it is actually strictly positive and it's strictly negative. That's very, very important. Okay. Of course, on any subinterval, it cannot vanish. The curvature cannot be constant on any subinterval. We have already assumed that. Okay. So the derivative cannot identically vanish on any subinterval. That is already there. So you're right. If you take these 2 points, then the sine curvature, the derivative will vanish because they are critical points. Okay. Now, so if I draw this red portion, it will be this portion of the rather I should have drawn the. So let me do the following thing. I should use red. So this is the red portion. Okay. And then I am interested in this line, in these 2 points, and I am interested in this line segment. Okay. So that is the line L that I am interested in, right? So this is the case when this is the case of only 2 vertices. Okay. Then there is one more case. There is a case of 3 vertices. So there is one more vertex. And as I already told you, if this one more vertex is a local extremum, then you have to introduce yet another 4th vertex, which will also be another local extremum. Okay. Therefore, we don't consider the case when the 3rd vertex is local extremum. So the 3rd vertex has to be a point of inflection. Okay. So let me write that. We consider, we also look at the case when we look at the other case. There is an extra vertex. Okay. Clearly this cannot be a local extremum, as it will entail the existence of another 4th vertex. So we assume it is a point of inflection. For the sine curvature. Okay. So now nevertheless, still the same argument holds. You can still break the curve into 2 segments on which the derivative of the sine curvature has opposite sign. Okay. And so you can see that. So what will happen is that you have again you have this interval 0 to L of gamma. Then you are going to have this point which we called as S0, and here this is Ks of gamma is global minimum here, and then you are going to have S1. At this point you will have Ks of gamma has a global maximum. Maximum here. Okay. And now let the third vertex be at S3. Okay. Now of course so let me draw this picture here again. And so this is my gamma 0. This is gamma of L of gamma, and then I have this point which is gamma S0, and then I have this point which is gamma of S1. Okay. And So we can look at various cases. So let me explain one case. So let us assume that, let us say, S3 is, let us say, here. Okay. Now if S3 is here again, so you see, apart from these points S0, S1, S3, at all other points the derivative is non-zero. Okay, because there are, all other points are not critical points. And again you use the fact that, what happens between a global maximum and a global minimum. So you see, if you look at it like this, you see from so let us say from S0 is a global minimum, then S1 is a global maximum. So I will get this portion. If you go from here to here, you are going from a minimum to a maximum. So certainly, here your Ks gamma dot is positive, okay, because you are going from minimum to a maximum, and there is no other point where it's going to vanish. So this portion I will again get the segment of the curve, okay, and here on this segment of the curve I'm going to get Ks dot gamma is positive, okay, except of course the endpoints, right? Then you see at the point S3, okay, the Ks dot vanishes, but at no other place. So there are two cases that you can think of. If you look at say if you look at if you look at this side, okay, you start going beyond S1, okay, what you will have is that see, S1 is a point of maximum, okay, and after that the function has to only decrease, okay. That means on this portion you see you are going to get Ks dot gamma is going to be negative, okay, and this will continue all the way up to this S3, okay, by continuity, because S3 is the point where next the vertex the next vertex occurs, where the derivative of the curvature, sine curvature, vanishes. And mind you, as you go from S1 to L of gamma, because it's a closed loop, you will again start from 0 and go all the way to S3. So this portion, so S3 has to be drawn somewhere here, okay. So so I'll put S gamma of S3 here, okay, and all the way from here to here when I go, okay, it is the other side. So you have Ks dot of gamma is negative, that is for sure, all right. The only question is what happens from S3 to S0, okay. The question is what will happen here. So if you if you look at this portion, okay, from S3 to S0, what is going to happen? So if you look at this point being a point of inflection, it's not a point of maximum or minimum, local maximum or minimum. So the sign of the derivative has to be the same on both sides. So it has to be only this case, okay. It has to be only that it is the same as what it is on the red portion, all right. So this is the only case I will get, and I anyway have so I anyway have this statement that whether there are two vertices or three vertices, okay, there is a line and there are 2 points passing through that the line passes through. These 2 points are vertices on the curve that divides the curve into 2 segments, and on these 2 segments the sign of the derivative of the sine curvature, they are opposite. So this is very, very important, okay. Now what you do is that you have to play with this line carefully and use the Fraunet-Serre relation to get a contradiction, okay. So how does one do it? One does it like this. So you see, you call this point as, so how does one go ahead from this point? So you see, you have this point, I'll call this as say P0, and then I'll call this point as so I think correct, I'll call this point as P1, okay. And mind you, there is this orange line which is L, which passes through P0 and P1. It cuts the curve into 2 segments where the derivative of the sine curvature has opposite signs, okay. Now what you do is that you take so I have to draw conveniently an origin somewhere. So it's just going to be gamma of S naught, of course. Okay, and now I'm thinking of gamma of S naught as a vector now. All right, then you take an arbitrary point on the curve. So this is gamma of S is an arbitrary point on the curve. So what I will do is that and if I join this, then I have this vector, this position vector, and this is going to be, you know, so if I call this point as P, okay, then so this is the OP vector. Okay, this is just gamma of S. Okay, and then you worry about, you know, this vector, which is of course gamma S minus gamma S naught. Okay, so that is a vector. Let me remove this L from here and put it somewhere here. Okay, and now what you do is, how do you use the line L? So you use the line L in the following way. So you see, you on this line L, you know, you take a unit vector which is perpendicular to this line. Okay. For example, you could have taken a unit vector at P, if you want, at any point perpendicular to the line at P0 or P1, really doesn't matter. All right, and the thing that you have to use is that from the picture, you see, as the point P lies on, you know, the segment from P1 to P0. Okay, you see that the P0 P vector is pointing more or less in the same side, on the same side, same direction, same side of the plane, the half plane divided by the line in which U points. Okay, therefore what happens is the dot product of these two guys, the gamma S minus gamma S naught and this U cap, you see, this dot product is going to be positive. Okay, and on the, if you move P to the other segment, they are on two sides of the line, so the dot product will be negative. So we have to make use of that. Okay, so notice that, you know, for P on the segment from, you know, P1 to P0, okay, gamma of S minus gamma of S naught, this vector dot U cap is greater than 0, greater than or equal to 0. Okay, so here, you know, let U cap be a unit vector perpendicular to L. Okay, so this L is which divides gamma into two segments. Okay, now you have from P1 to P0, this dot product is greater than or equal to 0, and if you go from P0 to P1, this dot product is going to be less than or equal to 0, and for P on the other segment from P0 to P1, you see gamma S minus gamma of S naught dot U cap is going to be, you know, less than or equal to 0. And when I see less than or equal to 0 or greater than or equal to 0, the equal to 0 will occur, you know, okay, so let me not worry about that. Okay, so so you have this. Okay, and you see the basically you have this dot product that is having opposite signs on these two segments. Then you also have the derivative of the sine curvature. That also has the same property, that it has opposite signs on these two segments. So if you multiply them, what will happen is you will get something that has the same sign throughout. Okay, all right. See this dot product gamma S minus gamma S naught dot U cap, that has opposite signs on these two segments. Okay, these two segments of the curve separated by this line. Also the sine curve, the derivative of the sine curvature, that also has opposite signs on these two segments. So if you multiply them together, you are going to get a function that is going to have the same sign throughout the curve. Okay, so that's what we are going to use. So thus you see, so maybe I will change the color to something that's more readable. Thus, if you take ks gamma dot into, mind you, this is a scalar function, into this this dot product, which is actually a scalar again. So you write gamma s minus gamma s naught, dot u cap. This has the same sign throughout gamma, and is of course not identically 0. Okay, all right. Now you see this is a function. It's a function that is not identically 0, and it has the same sign. So if it has the same sign, it means that if you take the modulus of the function, that has to be the modulus of the function is it's non-negative, it's greater than or equal to 0, and it's not identically 0, and that is going to be plus or minus this itself. Okay, because it's of the same sign. And the point is that if you integrate this, the integral is not going to be 0. So thus you see, integral from 0 to L of gamma of this function ks dot gamma of if you want, I'll put of s, of course it's understood, times gamma s minus gamma s naught dot u cap ds. This is not 0. This integral is not 0. Okay, because the integrand is of the same sign throughout, all right, and is not identically 0. Okay, so this is a very, very important fact. Usually if you integrate a function, the integral may turn out to be 0, because there may be portions of the interval where the function is positive and other portions where the function is negative. But if the function is throughout greater than or equal to 0 or less than or equal to 0, then the integral will also be greater than or equal to 0 or less than or equal to 0 correspondingly. Okay, so the integration will preserve the sign for the function. Okay, and of course the integral being 0 will happen only when the function is identically 0. Therefore, this is the condition that you come to. Now the point is, you can use the Frohn's-Array relation to contradict this. Okay, so from the Frohn's-Array you can contradict this, and therefore you will get a contradiction to the assumption that there are 2 or 3 vertices. Okay, and that will finish the proof of the convex case. Okay, to deal with the non-convex case, one has to do more work. There is a geometric proof due to Robert Osserman, and there is a more analytic proof that involves looking at curves on the Riemann sphere and their images on the plane. Okay, which was the proof given by Adolf Kneser. So this theorem was first proved by Syamadas, and then I think about several years after that, Syamadas proved it only for the convex case. Then the general case was proved by Adolf Kneser, and that involved something more deeper. You had to look at curves on the Riemann sphere, on the sphere. Okay, so I will stop at this point. I will need to use this and use the Frohn's-Array relations and say that this statement is contradicted. Okay, so that is what is left out. All right, you are saying continuous function on a closed thing, and you are integrating a continuous function on a closed thing. No, there is a problem. No, how is that correct? See, integrating a continuous function on a closed thing Just because the function has the same values at the endpoints doesn't mean that the area under the curve is 0, right? See, you are just saying that at the endpoints, the function values are the same. So you may have a graph like this, and there may be area under the curve. Why should that be 0? See, I can have, see, you can imagine that, right? So you have 0 to L gamma, it starts at some value, then it goes up, down, something like this, maybe on the same side of the axis, and then ends up at the same value. But the area under the curve, why should it be 0? It may not be 0, right? See, the reason where exactly the point where what you are saying is more or less correct. See, the fact is the integrand is actually the derivative of a function. Therefore, that function, evaluating this integral is taking that function and evaluating it at the endpoints and taking the difference. And that's where what you say happens. It becomes 0. So the Fronius-Area relation is used to show that the integrand is actually the derivative of a function. And you can just apply the fundamental theorem of calculus. Your idea is correct, except that it's not this function. It is d by ds of something else. And that d by ds of something else comes from the Fronius-Area. That's the whole point. That's the whole point. That's all. That's all the proof. There's nothing more. So, I mean, it's delicately you use the Fronius-Area. That's what you have to appreciate. Okay. Yeah. So we will continue to.